Yeah, this V slide.
Are you gonna print the notes or I can write down for them? I was going to today and I was running late. Thank you so much.
Yeah, no problem.
You're like only 1 week left of her.
Yeah.
Oh my gosh, thank you so much. It helps me. Not during the moment when I go back. So I write down everything and then I go back and I'm like, okay, what? What's going on?
One more week. Woo! How y'all feel about that? Tell if that was a nervous oh no or excited. Yeah.
It feels like it's gone so fast. I'm sad. Next year I have to be surprised, so.
Oh, I'm so excited about my next term. I have been going here this is my third term, and I haven't even touched a single one of my core classes for my program. Because they didn't have them up and running, so next term I'm doing like 3 of them back to back that are supposed to be staggered. I'm like, yeah!
What's your core again?
Cybersecurity.
Mm. That's right.
Yeah, I was trying to set it up so that way I could do it like one of them per term, but all the classes were like, last year, all the classes were like set up that they
Huh.
So Alan came on, right? Yeah.
I didn't realize Alan was that new.
Alan's, well, he was mostly advising, he wasn't doing a lot of teaching when he first started too.
Oh, I didn't know that.
Yeah, because it was mostly being taught by Rosie and one of the guys from Redwood. I have one of his classes.
Is he teaching here this summer? I forgot his name too, though. Were they
But
the
you know what
same?
I'm talking about, there's only one other person, but yeah.
Yeah, I know all the computer science people.
And then they just hired a new one too, right?
I'm not sure. I don't usually hear about
Rosie was telling me that they just hired a new one, because she was telling me that she was gonna be stepping more into the actual, like, because she's the head of the department, so they were having her step out of teaching as many classes and more into the head role. We'll see. It's been way too much time harassing Rosie.
Yeah, Rosie's awesome though. But...
Oh yeah, she is.
All right, I guess we get started. Oh, where's Alicia though? And she was just here too. I know Trey might be absent, so we'll start without him. This morning?
Yeah, when I was pulling in, he was walking down the road.
Oh.
I think he might have work or something, but I don't know.
Yeah, I mentioned like a DMV appointment or something.
That would explain why he was walking that way.
Okay. All right, so I think this is the point in the quarter or the summer quarter, mini quarter, where we all panic, right? I mean, so feeling okay? So yeah, this is our last week. Maybe you're ready to be over. Or last week of class, question mark. So of course we still have, right, 2 more weeks of the quarter. So this week our goal is to finish up the lectures. We may tail into Monday with chapter 9. We'll just kind of see how that goes time-wise, but I'll try to leave some review time. But that leaves us with, right, our final exam next Thursday. So that's kind of next Wednesday, thank you. I forgot what days y'all were on. I've got Tuesday, Thursday on my brain for some reason. So next Wednesday, your final exam, and then we're also doing a lab final. That should be relatively straightforward, and we'll do that in our kind of lab period on Wednesday as well. And we'll do checkout, I think, then as well. That will be part of your lab final. Yeah, just looking at your drawer, making sure it's clean and the everything that's supposed to be in there is in there. And you won't be penalized for it, right? You just got to hunt down what you're missing, or if you're a hoarder, you need to donate back. Well, so we'll figure out if anyone's a hoarder. Any other things? Oh, we do have one homeless homework. So chapter 6 energy homework, I couldn't quite tell whose it is. The handwriting. Kind of looks like yours, but I'm not sure. Double check the blackboard grade. It's yours? Cool. So I'll enter your grade in. But while y'all are quizzing today, I'll hopefully be handing back all the papers that I have. So I think I caught up on the grades. And then double check, of course, your Blackboard grades, that everything is accurate there too. All right, if there are no questions, then let's dive into chapter 8. And so I've kind of been teasing chapter 8 with the moles, but now we're looking at it. And so this is solution chemistry. So when table salt is mixed with water, it seems to disappear, and that's because the mixture becomes homogeneous. And of course, the salt is still there, so you could taste it, no taste salty. And then we could re-separate them, right? This is why this is a physical change as opposed to a chemical change, because you can get it back out, boil away the water, isolate the salt. And we've looked at homogeneous mixtures before, and we can also call them solutions. And so the minor components, so this is usually what you're dissolving. So the minor component is your solute, so this is whatever you're dissolving, usually your organic compound, or in our case, right, we use a lot of those dropper bottles, so it could be like iron chloride or some metal in water. And so that means our major component is called a solvent. And so AQ, that means our solvent is water, so that refers to any sort of aqueous solution. But in organic chemistry, they use a lot of, obviously, organic solvents, so ether, benzene. This is not encompassing either, so etc. And this has actually been an area of research, but it keeps coming up to the forefront, is converting all these organic solvents. Can you do the reactions in either less solvent, no solvent, or trying to get them to do them in water? And we won't go into why that's difficult, but cool area of research. Anyone wants to do research? All right, colloidal mixtures. So colloidal mixture just refers to two mixtures. And so usually these suspensions end up having some sort of Tyndall effect. These solutions tend to be like cloudy or opaque. Or we'll see like cheese and mayonnaise can also be colloidal mixtures, and those can be pretty opaque. And so that's due to the particles being large enough to scatter light. And if you were to do this with like a gold solution, and this picture doesn't really do it justice, but if you were to kind of look at the solution and turn it around and hit the light with it, it would really reflect and be pretty shiny. You would be able to see all those crystals just kind of floating around suspended. And let's look at other examples would be, like, y'all have seen, of course, right, you blow some smoke or from a fog machine, and you know how that scatters light, or even when it's really foggy, that scatters the light everywhere and makes it hard to kind of see. So all that is the same thing, the Tyndall effect of just large particles scattering light. And so these are just different kind of systems. So you could have a gas and a liquid, again, like fog or mist or cloud. So as we approach Halloween, right, you can think of making your own colloidal mixture with some fog machine. Gas, solid, so that could be, again, same thing, dust, smoke. And I'm sure you've seen that. Maybe you're dusting, you smack your couch, or you shake your duster, and all those little dust particles, right, they scatter the light, so same thing. So that's the Tyndall effect. And other systems, so if you have liquid and gas, like whipped cream, shaving cream, that's also a colloidal mixture. Paints, mayonnaise, all that, so those would be like liquid, some sort of emulsion. Liquid solid, this is going to be oil-based paints or some sort of pigments. And solid gas, so pumice stones, and you know those pumice stones, how they have little holes in them, so that of course is formed from that mixture. Then cheese, so that would be a solid liquid mixture, or gelatin. Then solid examples would be ruby glass, where you have some sort of impurity giving you those pretty colors. So let's look at solubility. And we've kind of touched on it with our precipitation reactions. And so we'll look at two solutions. So a salt water versus a sugar solution. And of course, salt water is just a homogeneous mixture of sodium chloride and water. And sugar water is sugar and water. And so we have this kind of saying, like dissolves like. And so let's look at what does that mean on a molecular level. And so what happens, so you have, of course, right, your solute-solute interactions, so your little particle interactions that you have. And these could either be, right, your intermolecular forces, so we discussed that, or if you were sodium and chloride, those would be those electrostatic forces just brought on by the ionic bond. And then can your solvent-solute interactions, is this large enough to overcome then your solute-solute? And if so, then it solubilizes. And so the words just go through that. So again, your attractive forces hold your solute particles together. So again, could be sodium chloride, could be our intermolecular forces like sugar. And then our attractive forces between the solvent and the molecule, of course, rips it apart. And so that's why if you had, right, some polar molecules holding each other together in this solute, you'd want a polar solvent, right, like dissolves like, so it has similar forces and can overcome like those dipole-dipole or hydrogen bonding interactions. And so we've seen this before, and of course, right, water's polar property comes back, and this is what makes it such a great solvent. So we've seen this, we know that it has an uneven distribution of electrons. We can redraw this, right, in its Lewis dot structure. So we can see those lone pairs. So there's our electrostatic potential map showing us the same thing. We can add our partial negative, add our partial positives to help us. And so let's see what that does, of course, in solution. And that means that our negatively charged side of our oxygen is attracted to, of course, sodium, and that can overcome then this electrostatic potential between sodium and chloride. And of course, at the same time, right, chlorine is also being attracted by our hydrogen. And so this is strong, and of course dissolves it. And so this is on a molecular level, what this would look like. So of course our big chunk of sodium salt, and this would right appear like a big crystal, or it could be a little crystal, right, floating around or maybe sinking to the bottom. That's kind of like our precipitate that just forms, right? It's just kind of existing. And then again, if it's coming out of solution, that's where, because I noticed a lot of people, you know, said like, why is it fuzzy or cloudy if it's solid? And that's because it's just coming out, right? You may just be at the limits of solubility. And so to us, right, it kind of looks fuzzy or weird or cloudy, but that's just because it's just dropping out of solution. And then if it's going reverse, so now it's kind of doing the other thing. So you start with something solid, could be small, little chunks, you know, like think of your salt crystals. So they're already kind of small, although you could dump a big chunk in, but then you would just watch it dissolve probably more slowly, right, because of surface area. So big chunk sinks to the bottom, and then you're thinking about, so those surface interactions are going to happen first. So again, surface area matters, and then it'll start dissolving that little sodium chloride crystal. And so back to, if you did have something cloudy and you wanted to get a precipitate, that's where you keep kind of adding whatever that chemical is that drives the precipitation. So maybe, right, you're trying to get out silver chloride, so you need to add more silver nitrate or something to try to precipitate out a nice solid chunk, so then you get a solid. And that's where the art of chemistry comes into play of crystallization. So you played a little bit with that sodium acetate. You saw how that was kind of weird and made those jagged crystals. And so part of like chemistry is like taking something, dissolving it, getting it in solution, and then cooling it back down, and then making like nice crystals that you could actually mount an X-ray. And that's how you get the structures. We did this in here, right, with the demo?
Yes.
All right, just checking. So we went over that. And so just a quick recap. So we said that materials that dissolve in water, that form a solution that conducts electricity are electrolytes. And what type of compounds were those? What else could we call them? So they are the solute, but I'm looking for another word. Like what type of compound or... So I guess I'm asking, is it an ionic compound or a molecular compound if it's an electrolyte?
I said ionic, but you didn't answer, so.
Oh, I didn't hear you, sorry.
Probably wrong.
I just didn't hear you. And nobody jumped in. All right, ionic, sorry. So ionic compounds, so those are electrolytes. And they always have some sort of positive, some sort of negative charge. And so those non-electrolytes, what are those also known as then? Yeah, so our covalent molecules. So those are all our non-electrolytes. So we remember that. And so comparing the interactions, so this dissolves pretty readily, again in solution since it's charged. We kind of have gone over that. Then if we look at sugar, so sugar does have, right, some OHs on there, so some hydrogen bonding. And so we can get some solute-solvent interactions at those points. And so, right, sugar does kind of go into solution, so there it's showing it what it would look like more solubilized. So this sugar is surrounded by the water molecules. But you can kind of see, right, that's more difficult. Just imagine how many more water molecules that takes to kind of surround and solubilize it versus, I mean, this is, it forms, you know, much more readily isolated with just that one atom that they can all easily surround versus, right, this larger molecule that they're trying to solubilize. And that's also, you can heat it. So many of you have done that before. Heat a sugar water solution. You could make, right, simple syrup from that saturated solution. So that's how you make it, right, get enough hot so where it stays in solution. So electrolyte solutions are then classified how they dissolve. So if you have a strong electrolyte, this means it completely disassociates. So again, this is usually your ionic compounds as long as they are soluble. And under here also strong acids and strong bases. And weak electrolytes just mean that they have some sort of partial disassociation. And the most common example that we look at and that you're familiar with is vinegar in this case. So this is formate. So let's draw this out. So formate is this molecule. usually vinegar is the other one that's given. So this is a carbon here. It just has another carbon. So same thing, vinegar is considered a weak acid. This is also called acetic acid. So this will probably come up later. And again, notice the equilibrium arrow. So this is drawn funny in the notes. It should be just a half arrows. But again, equilibrium, so it goes back and forth. There's still some completely associated and then some disassociated. And then molecular compounds that dissolve in water but do not form ions are called non-electrolytes. So those are most of our molecular compounds. All right, so this just reiterates kind of the same thing. So going through our strong versus weak electrolytes. So again, emphasizing sodium chloride would fully disassociate. So anything that's soluble on your like precipitation chart that you have, so all those, right, would go into solution. Everybody know what I'm talking about? Like the solubility chart. I did at one point. I have copies somewhere, or I can make more if you need. Yeah, so as long as it's soluble, if it's fully soluble, it's going into solution, that would be an electrolyte. And so we'll revisit acids and bases in our next chapter, but those are just compounds that, again, they disassociate. And so some of our strong acids are going to be HCl. Nitric acid is one, or at least and phosphoric acid, so the first disassociation, sulfuric. But we'll look at our acids in our next chapter. And then here's acetic acid, so we mentioned this would come up. So acetic acid, which is again vinegar, is a weak acid as it partially disassociates in water. And you can compare the little pictures. So HCl, all of their HCl molecules are split. And if we look at our weak one, some are all bound and some are disassociated. Kind of hard to tell from the Sabal structure, but and again, sugar and other molecular compounds are non-electrolytes, and most molecular compounds, except acids and bases, dissolve in water as intact molecules. And so this would mean like organic acids and bases would be in the weak acid category, but we probably won't worry about that. We won't get into that too much, but just kind of an FYI. So we saw the light bulb, so we've been through that. We can always pull it out again. Of the electrolyte, the weak electrolyte of vinegar, and then you could test out either sodium chloride or a strong acid. And you would also see the brightness should change with molarity as well. So if you have a higher molar solution, you should have a brighter light bulb. And so this goes back to your solubility chart. So this is where it's formally covered in the lecture notes, but we've been kind of dancing around it. And so it says, right, not all ionic compounds dissolve in water. And so we've seen silver chloride before. And so silver chloride, if we make it from a reaction, then we know that we start to get some sort of white cloudy precipitate or white powder. If you, what's called crashing it out, then you would get like a big powdery substance at the bottom. And so if a compound is soluble, then it dissolves, and insoluble if it does not. And that's where you have to look at a chart for it. And so this is why your chart may seem kind of confusing sometimes. So when will a salt dissolve? So of course it depends on several factors. So of course it's just based off of that basic, right, solute-solute versus solute-solvent interactions. But it's not always easy to predict. And so of course the best way to do it is just do it experimentally. And so a lot of being a chemist is just like playing with different solvents too, trying to get things to dissolve in one thing and crash out in another solvent. So really just trying to play with solvents. And your solubility rules should look similar to these. If there are discrepancies, it's probably because a compound would fall like right on the line, like calcium sulfate tends to be one of those weird ones. Like a lot of the sulfates, either you see discrepancies in the rules, and it's just, they tend to be kind of on that line of are they soluble, are they insoluble? And if you were to take the 200 level chemistry series, you would quantify this more and actually put like some numbers to these solubility values and get a better sense of. Usually not. So sulfates are different, so they're pretty common, right? Sulfur oxygen compound. But like sulfas, yeah, so sulfurs are just like used a lot in drug compounds because sulfur can attack like the.
I just see a lot of allergies to sulfa drugs. So it's sulfas and drugs,
Yeah.
just the sulfa aspect of it.
Yeah, different group though.
Okay.
Yeah, because sulfas have to have like a lone pair because sulfates are all. I'm trying to find. And pulled up sulfonamides at least to compare if you were curious. So it's slightly different, but yeah, back to solubility rules. So you can kind of see your alkali metals, all these tend to be soluble, right? Ammonia tends to be soluble. And no exceptions, same thing, right? Nitrate and acetates, those are always soluble. And so chlorides, bromides, iodides, all those when paired with silver, mercury, and lead are insoluble. So notice your kind of heavy metals. And then sulfate, so strontium, barium, lead, silver, calcium. And again, barium, calcium are usually those weird ones. Sometimes magnesium is considered insoluble. And then hydroxides and sulfides are generally insoluble, and except if they're with alkali metals and hydroxides. So these are also kind of weird. The hydroxides with calcium, strontium, and bromium are all considered slightly soluble. And if you wanted, you could of course get a sense of solubilities. So I pulled up a few. So you have magnesium sulfate here. And so it has different solubilities depending if it's the anhydrous version, so that is about 26 grams in 100 milliliters, or the heptahydrate is 113 in about 100. Let's see, calcium hydroxide, solubility, so 1.189 grams in a liter, so that's pretty insoluble, at least in my opinion. Silver chloride, just to compare, it's pretty insoluble, so 520 micrograms in 100 grams, and that's even hot, so they didn't give it to you at room temperature. So that's kind of that one. And so that at least helps you put numbers to the soluble, slightly soluble, and that's where, again, the weirdness comes into. Again,
Even though it's like micrograms, that's little, but that's still just all in those slightly soluble.
well, that's why they have silver chloride as insoluble.
Okay, that's what I was thinking.
Yeah. But yeah, some amount will go in, and that's where,
Even in unsolubles, sometimes a tiny amount will go in. But
yeah. Yeah, because some amount is going in, and that's where the Chem 200 level series gets into just a little bit more of like the math and quantifying and putting KSP values. So that's what this is. The KSP relates to the solubility, so you could calculate one from the other, basically.
Okay.
And yeah. Yeah, so when you're ready to quantify it, and so
Teach the next one?
I do. So you're stuck with me.
Right.
Yeah. Unless you want to go to Grants Pass, they teach it the same course there.
I'm using a chapter of the GI finding that basically means that I'm not allowed to take anything outside my career path.
No.
So I only needed one science for my degree, so they won't authorize anything, even if I really want to.
Kind of a bummer.
We'll convert you to
The poor teachers.
cybersecurity chemistry. Well, anyways, you can only see sodium chloride is 360 grams in a liter that you can get in there. So that's a lot more soluble. And carbonates, phosphates, these are also generally insoluble. I think we kind of saw that in lab. And again, right, lithium, sodium, potassium, ammonium, those are all soluble. And so that kind of explains why all your dropper bottles are usually, right, lithium, sodium, potassium salts that you mix. So maybe this is all coming together. All right, so let's take a minute or two and predict whether these compounds are soluble, insoluble, and we'll go over them. to do it.
I have to find the program.
You could talk to Kevin Murphy. He actually did computational chemistry in grad school.
Really?
Yeah, he used to teach chemistry, and now he switched over to math here. But
We're just looking at the charts.
yep, yeah. And I can zoom out on these too. Oops. I don't have a chart handy. I can print another one later. We go over them. All right, lead chloride, soluble, insoluble? Insoluble. So is that what everybody got? All right, so chloride when it pairs with lead, insoluble. What about B, or copper chloride? Anybody?
I guess it's soluble.
Yeah.
I don't see the copper anywhere on here, but it doesn't hit the exception, so I just guessed that since it didn't hit the exception, that was.
Yep, exactly. And I'm pretty sure we've seen copper chloride in our hands at some point from the stock room. Yeah, one time we scared some safety people because a copper chloride solution was crystallizing out. So, I think of safety people. All right, calcium nitrate.
I guess soluble, just because the NO3 has no exceptions.
Exactly. I'm gonna roll with that one. And what about the last one, barium sulfate? Or, yeah, sulfate. Yep, so insoluble. Excellent. Any questions on those? And this chart just tells us that for the most part, as we heat things up, they become more soluble. And right, you can just put something, so in general, for solids, right, temperature increases, solubility increases. So there are a few exceptions with like the cerium sulfate, so I'm not entirely sure why. So we'd have to look at this more specifically and try to understand, because what it's saying, right, is that the interactions between itself, so the solute-solute interactions, are getting stronger versus the solute-solvent interactions. So that's a weird case, but again, everything else increases. I don't know exactly. I would have to like actually dive into a paper about it or something.
Well, somebody dove into it already.
Yeah. Although assuming you can make it past the paywall. Or see what. I know, that's how you gotta do it. Blah, blah, blah. And so gases, you wanna note, so gases are the opposite. So this is what's kinda weird. And so for gases, and it's just the opposite, so as temperature increases, solubility decreases of gases. And that's, they're in different phases, so that doesn't help. So of course, as the water or whatever your solvent is gets hotter, then your gas tends to kind of come out of there. And you can see this in the illustration or the picture of the soda. So the cold soda, right, it's not super fizzy, and the CO2 isn't leaving since it's still dissolved in there. Meanwhile, the warm soda, as soon as you pour it, right, it's all coming out, and then it would be flat faster. Yeah. So depending how you want your soda, if you like all your bubbles initially, I feel like some people like that warm bubbly soda, Okay, maybe not. And so for gases, the solubility of the gas decreases as the temperature increases, and that's because our delta H is exothermic, since we don't need to overcome our solute attractions. They're already coming out. And so of course, how can we make a solvent hold more? So if we're talking about a soda, then of course we can pressurize it. We can make our solution super saturated. You have done this maybe personally with making rock candy. That's always one to do with your kids and talk about the super saturated solution. And then, right, you make nice crystal formation with your rock candy. And so super saturated solutions are unstable and lose all the solute above saturation when distributed. And I think you guys are pretty good at this. You mentioned how you could freeze water too at the limit of crystallization. So if you have cold water right at 0, if you like smack it at the right way, it crystallizes. You kind of saw that with the sodium acetate. Or you guys have played tricks, I'm sure, with beer bottles, soda bottles, making things come out of your solutions.
So is it just because you're tipping over that energy barrier, like with water bottles, when you get like a water bottle like that, and then you smack it and crystallize it? Is it just because you're helping to break that energy barrier?
Yeah, that one's kind of weird because it like crystallizes. I'm not quite sure why smacking it gives it. I think it like just gives it also a nucleation point too, because when you put something in there, like the crystals can nucleate off of it. But yeah. And so then we can quantify our solubility of gas with Henry's law. And this is fairly straightforward, so you can see it's dependent on the gas constant. And we have solubility S, and this is usually given in molarity. And we'll go into molarity. And you would have to look up the gas constant for each gas, or I would give it to you on an exam. And so our Henry's law constant for CO2 at 25 degrees Celsius is 3.14 times 10 to the negative 2 molarity per ATM. So depending on how much gas you want to put in your soda, all this is telling you at what pressure then you'd have to pressurize that at. All right, so concentrations, this is probably the meat of the chapter. And so getting into how we quantify them. And we can kind of call things dilute, concentrated. And these are just more terms that are thrown out there. I'll say dilute is usually less than 3 molar. And concentrated would be greater than. Again, that's just rough. But we'd want to, of course, actually give an actual molarity and not just say dilute, concentrated. Usually this is more like safety, like concentrated, you want to wear more safety stuff. But that gets into actual handling. And so let's look at our concentration units. So this is the big overview cheat sheet, and then we'll kind of go into all of them a little more. So we'll look at all of them. So we mainly use molarity. This is what's most common in chemistry. That's what's put in all the bottles in the stock room. So that's moles over liters. Sometimes you'll see a molality. This isn't as common. And obviously they're just one letter difference. So, watch that. And then it's a little m, so that's the other difference, the little m molality. And that would be moles over kilograms. Sometimes this is considered more accurate since volume can change a little bit based on temperature. But again, molarity is usually just a standard. So we have mole fraction, mole percent then, part by mass, and parts per million, parts per billion, and parts per volume. So let's look at all of them. And so this is also how to prepare a solution properly. And so let's say we want to prepare a solution from a solid. So of course we have to know, right, the amount of solution and the concentration. So this is where moles and everything is going to come back to haunt us as well. And so in this case, looks like they're doing a 5% mass per weight solution. So that's going to be 5 grams in 100 grams of solution. So there's your 5% mass. And so we need to first dissolve our grams in solute. And so what you do properly is, so in this case now, they're making a 1 molar sodium chloride solution. So you'd weigh out your mole, pour it in there, and then you want to add enough water, probably to about here first, so not all the way. Then you get it nice and dissolved and homogeneous, and then very carefully you add enough water until you reach the 1 liter mark. And so that's another thing when you're preparing these solutions analytically, you have some sort of volumetric glassware. And so this is really precise, and it's really precise, but it's only good for one measurement. So like this one's only good for 1 liter. If you wanted 500 milliliters, you'd have to get an appropriate volumetric. And this isn't shown properly, but they usually have a little stopper so you can cap them and shake them. All right, so now let's look at molarity. So like I said, this is probably the most common one you'll see. So molarity is, again, moles per liter. So you might want to just write that somewhere, or just because this will come up a lot. And so again, molarity describes how many molecules or atoms of solute are in each liter solution. So if we have a sugar solution that is 2 molar, then 1 liter of solution contains 2 moles of sugar, and 2 liters contains 4, 0.5 is 1. Again, it's just this ratio, moles over solution. Does that seem straightforward, right? And we'll do practice, because this is where again, usually people don't have trouble with the molarity. It's relating the molarity back to the good old balancing equation type problems we've seen in stoichiometry. So then we have molality, and again, molality with our L and our little m. So that's just moles per kilogram, and again, it's kilogram of solvent and moles of solute. And molality is defined in terms of amount of solvent, not solution. So that's also important, right? So that's amount of just your solvent, so that means not the total solution. And so that's kind of the distinction. So again, going back to how you prep the solution, right, for the molarity, you're always equaling up to the same volume versus molality, it's per kilogram of solvent. So slightly different. And so again, that's why some people say it's a better measurement since it does not vary with temperature, since it's based on mass and not volume. But in practice, I really never see anyone use molality. So it's not in my experience. Maybe in your future you'll see that. Yeah. To molarity? Yeah, because it's only a subtle difference, and it's more like when you're making it or when you're totaling the liters. So sometimes you have to be careful if you're like starting with something and you're doing a dilution, and then you need the total liters of solution. And so then we can have parts, and so parts can be by mass or by volume, so that's where you always have to watch the units. And so parts are generally in the same units, so mass in grams per gram or kilograms kilogram, or volume, so milliliters per milliliter or liters per liter. You may also have a percentage, and right, a percentage is just ultimately parts over 100 parts. So in this case, it's 0.9% by mass, and there's 0.9 grams of solute in every 100 grams of solution. Of course, you can scale that right to kilograms. And so parts per million, which we'll look into, is just parts then for every million parts of solution. And so again, parts per million, so 1 over 1 times 10 to the 6. But another conversion that we can use for it is we can do, right, milligrams over kilograms. So this gives you a 1 times 10 to the 6 factor. So milligrams is, of course, 10 to the negative third, kilograms 10 to the third. Oops. So there's your, right, 10 to the 6 right there. So you could convert whatever you're dissolving, your solute, into milligrams, and then convert that to kilograms, and that's parts per million, or convert back and forth, if that helps. And so again, here's shown milligrams per kilograms. And so that means for parts per billion, so 1 over 1 times 10 to the 9th now, I would convert that, so parts per billion would be micrograms then per kilogram. So if you use this factor, so convert whatever our solute is to micrograms, and then put that into kilograms of solution, there's our 1 times 10 to the 9th factor. So mole fraction is fairly straightforward. So it's just whatever fraction we're interested in of one component over the total moles. So in this case, we have our mole fraction for A, and so that means moles of substance A over our total moles, in this case A plus B. And so this means it is unitless. And then of course, right, we could take this mole fraction and multiply it by 100, and that just gives us our mole percent. So you could see these given out, you know, the mole fraction is this, or mole percentage. So those are used pretty interchangeably. All right, so now more math, but this is super important and really what the stockroom does a lot, especially for us. And so part of the stockroom's job, or if you were to be a lab tech or something or work in a lab, is of course you have to take your stock solution, which is usually something really concentrated, so generally it's about 12 molar, and then you want to dilute it down. You know, a lot of times we work with 1 molar or 0.01 molar solution, so they have to really dilute that down. And so you can use this simple formula. So concentration, so our original concentration times whatever volume of the original solution is equal to our new concentration times our new volume. And so usually you would back calculate V1. And so, right, our stockroom has to go, okay, this summer, you know, Marissa has 7 students in her class. This is how much solvent they're going to need for this experiment. So they would be calculating, right, V2. Okay, based off of these students, we need this volume. It's going to be at this concentration from the lab manual. And then they just figure out, right, V1 from whatever stock solutions. And you often see these formulas written interchangeably. So this doesn't matter to me. So notice this one's kind of more general. So concentration can be in any units as long as they're the same. So notice that for volume. So it can be milliliters, milliliters, you know, gallons, gallons, whatever, as long as it's consistent. So same thing, concentration, usually we're in molarity, but it could be anything else, percentages, parts per whatever, just as long as it's consistent. But then you'll often see people give this more specific formula as molarity. Again, doesn't matter, they're the same. All right, so now see if you can do the math before I scroll down, because it will probably reveal. But it says we want 3 liters of a 0.5 molar calcium chloride solution, and we're starting with a 10 molar calcium chloride solution. So determine what's essentially, right, our V1. So see if you can calculate that. have answers? So I'll at least sketch out, so we should have plugged in, so C1, B1 equals C2, B2. So these were our desired ones. So again, maybe they're prepping for one of our labs. They need 3 liters of this, a 0.5 molar solution. And so starting with a 10 molar stock solution, solving for V1. And again, as long as all your units are consistent, we don't have to worry. So what do we get for V1 then? How much original stock solution do we need? So 0.150, so that equals V1. And so that is in liters. And so yes, that's what is revealed here. And so again, this is just going through the proper method to make it. So you measure out your stock solution. Arguably, this is not the best way to measure it out. That's my minor criticism. But maybe that was their most accurate piece of glassware. And so then you put in your concentrated solution first. And then you'd probably want to dilute it right up to here first. Shake it up, get it homogeneous, then fill it up, and you have to go again drop by drop. So if you were to pass up this mark, then you have to start all over basically, since it's ruined. So you don't want to go over that line. And there's your final solution. Questions about this first problem? Okay, let's try another practice. So to what volume should you dilute 0.2 liters of a 15 molar sodium hydroxide solution to obtain 3 molars sodium hydroxide? Was it a cat or a siren? I heard him, I think. I don't see anything. We have, we're getting a hedgehog too. Oh, and we do have hermit crabs now that were just purchased. Yeah, we used to have a hedgehog, but he got really old and passed away, but we're getting a new one apparently.
My other dog depressed, I would have brought my service dog with me. My service dog turned from my service dog into my other dog's service dog. Now I can't take them apart.
Oh no. Do we have answers? What do we get?
Filling off like off 1 liter. Okay, cool.
So everybody got 1 liter.
It felt 2 liters to be right, but I guess it works.
So 0.2 liters, so 15 molar equals 3 molar of volume. And, yep, so volume equals 1 liter. So 15 times 2 gives us 3, so yeah, that's how it worked out so nicely.
Good. When it works out nicely like that, it usually
And I probably should have put some sig figs on that one. Yeah. Here we go.
Is that a B?
V here?
Yeah.
Yeah. V for volume.
So why did we change from like I probably missed this, but why did we switch from N to C?
Oh, C is a general concentration.
Okay.
So, yeah.
So C is talking about the concentration of dilution, where N is talking about the moles.
Or, yeah, N is moles, yeah. And then we'll have molarity and molality.
Okay.
All right, so last little bit of the chapter at least, and then looks like we'll have time to do some practice. At least we blew through this chapter. So freezing point depression. So the freezing point of a solution is lower than the freezing point of a pure solvent. So I think most people know this just from the fact that we put salt on the roads to de-ice them, so that just lowers the freezing point, so then it melts. Of course, I discourage the use of salt since that's probably bad for the fresh water. I notice around here they use like red clay or something a lot. So that's probably more environmentally friendly. But again, we can quantify it. So it's just based off of this freezing point depression proportionality constant. So of course this depends on the solvent. These would all be things you have to look up or be provided. And then notice that these units that they give you here are in molality. So that's a little funny. So notice that. So again, and we could write this out. So molality was moles per kilogram of solvent. So just note that, so we don't often see molality. But you could get a KF in other units too, so if you just start searching around the internet, just be aware of that.
If 1 liter of water equals 1 kilogram, typically, so isn't molality and molarity, is it like you get back and forth in essence?
Almost, yeah, except like it's like off by a tiny hair, yeah. Which is, I'm sure, why the analytical chemist would argue that molality is better, but, you know, I would argue like, it's probably, unless you're an analytical chemist, you're probably messing up anyways. And yeah, analytical chemistry is just, I don't want to say it's like a different beast, but like in some ways, like it really is. Like you have to be super precise and glassware and everything. Gets you paid though, at least with a bachelor's. All right, so looking at this, so this is just why it happens. So adding salt disrupts, of course, the equilibrium, right? So it disrupts the packing. So we're thinking about our intermolecular forces, and anything that is different usually disrupts that packing. So of course, right, that means to get back to equilibrium, aka back to freezing, then we have to lower the temperature even further so that the water molecules can slow down and attach themselves to the ice with the salt, of course, in there as well. And again, just appreciate it as a chart you would be given. And so you can kind of navigate the chart. So what you care about is your freezing point, since you would be calculating your deviation from freezing point. So you calculate, right, how much lower, and then calculate your new freezing point, that should be, again, lower. And then you have your KFs, again, notice your units on molality. And so notice we're probably gonna talk about boiling point in just a second, since we have boiling point values. And so let's do a little calculation. What do you mean by special? What? I think it just has a higher,
Well, that's what I'm saying, normally we were saying that, so it says that solutions that have a lower freezing point than water standard, but it actually raises the.
oh, so this is if the liquid though, so this is
Okay.
freezing point depression, so what this is saying is benzene has a freezing point of 5.5, and then its KF is 5.12, so it'd still be depressed,
Okay.
yeah. And so try this one, and then this one, notice the keyword of aqueous, which might help. How's it going? So we just had to use this KF, right? So this was a little tricky. They were trying to trick you by just saying aqueous ethylene glycol. So right, ethylene glycol is our solute. So aqueous means that H2O is our solvent. So then we're just looking at water. And so then I'm just going to plug in for our KF. So remember that's our delta T. So how much it's being lowered is equal to, so I'll first just write out, it's our KF times our molality. And in that case, it's 1.86 times our 1.7. And what does that give you? I don't have my calculator pulled up. So 3.2, so that's our delta T, but then it asks for freezing point, and of course, water has a freezing point of 0, so then we can say freezing point is negative 3.2. And again, your freezing point is always lower of your solution. So freezing point depression,
What's next line, K? K,
little m as in molality.
oh, okay.
So just kind of following with our units here. So we need to get out Celsius to how many degrees. So we multiply by our molality. And so we have freezing point depression, and so that gives us boiling point elevation. So now the boiling point of a solution is higher than the boiling point of a pure solvent. So if you wanted to have an argument with a chef, you can argue about whether you add, the salt before or after. And I've heard all sorts of different arguments for both, so I have no idea what if it truly makes a difference. So some people say, right, you add the salt in first, but then you have to heat it to a hotter temperature. Yeah.
In terms of cooking, at least, I actually saw a video that said putting in the amount of salt that you do to help the water boil faster, it doesn't actually matter. You need to add a lot of salt in order to affect the boiling.
Yeah, so
For
we,
somebody who cooks with salt regularly, you wanna, just a quick fun experiment, get your water boiling for like pasta, and then add salt in, and you'll watch your rolling boil just instantly. It's a quick, fun way to do it.
Yeah.
Like, legitimately, because I pre-salt my water for my noodles, so that way they don't stick, and you'll literally have it roll boiling, I'll add my salt in, you'll just watch it die down, and after heat it back up.
yeah, so it would be fun to quantify it, like you said, because I've always wondered that, but I've never done the math, because I've never bothered, like, quantifying how many grams people normally put in versus a solution.
I have a candy thermometer, I can put it in water, see the boiling temp, and then throw some salt in it.
And then you need to measure how much salt you added, though, and how much water approximately.
I've measured stuff, I can throw a liter of water in, and like, 2 tablespoons of salt.
But yeah, then there's the argument then of, is it better to have the water hotter, and then so your noodles are cooking at a slightly higher temperature with the new boiling temperature of the salt, or does it cook it through fast? Is it negligible, like you said? So people like to have all sorts of arguments like this, salt it before, salt it after, for that reason. So maybe we'll revisit this boiling topic. Sounds like we need to cook pasta in class. I know. I proposed that, actually. I don't know if the deans bought it.
Sticking with home ec.
Yeah.
That would be the one humanities class I'd love to take.
Yeah, cooking and chemistry would be fun. Then you could do all the egg substitutes too and compare. Anyway, so like we saw, our KB constants are pretty similar. Again, we're getting them given to us in degrees Celsius per molality. And so now let's look at this problem. So now it's a little bit trickier. And I'll probably have to scroll back up so you can get your KB. But what mass of ethylene glycol in grams must you add to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius? And they at least give you a hint that your delta T for boiling is 5. And then you may want your water. And I can just copy your water KB, 0.512. Yeah, so M is in molality.
I think it is poor move on its way off, where I think I might have finally lost.
So
I
let's,
don't know where I'm at. I have a number, but I'm not sure.
so let's,
There's only two options, it's either right on the point or I'm way off.
well, let's walk through it together. So what did you first do?
Well, first I tried to figure out my ratio for my molarity. So I took the K equals C over M and turned it over, so that way, so the K was the 0.512 equals the 5-degree change over M. And then I did my inversion for algebra, which gave me uh, 5 for M equals 5 divided by 0.512.
So then what's your M?
My M was 9.8.
So 9.8.
And then I took that, and I mean, I guess it was pretty easy because he gives us exactly 1.0 kilograms of water. So I took the molarity equals moles over kilograms. So I took the 9.8 equals moles divided by 1 kilogram.
Moles moles over kilogram, and then we had 1 kilogram, perfect.
So I times both sides by 1 kilogram, which gave me 9.8.
So that's looking,
Is that right?
yeah.
Okay, you didn't tell me I was way off, so
And then, so then we need it in grams still.
oh, yeah. I hadn't made it to that part.
Nah.
I was just like mentally just happy I made it to that, okay.
So where did we all, did we at least make it to here maybe?
So then I can figure out the rest now, okay, cool.
So this was just, and we could, I don't know, let's try to rewrite this, because we have 5 is equal to, right, KF times our molality. And so, right, 5 is equal to 0.512 times our M. So just recognizing that you're solving for molality. And then you could divide. So this is like step 1 is getting there. And then, yeah, step 2 is just like rewriting your molality as moles over kilogram. And then we were given 1 kilogram to maybe make it easier. And so we're already at 9.8 moles, so we just need to convert this to grams. But now we're going back to what was originally said as maybe the salt is negligible. So we're looking at even in 1 kilogram of water, we're adding 9.8 moles to get something that's at 105 degrees Celsius. So maybe our salt in our pasta water is negligible. So do we have, what's our molecular weight of ethylene glycol? Let's do that first. 62 grams per mole. Yeah, that's fine. We can take some liberties. And then 62 times 9.8, about 610 grams. So that is 62. So, yikes.
610 grams of salt for 1 kilogram of water.
Yeah, I mean, roughly. Yeah, I would still love some quantification, but anyways, probably negligible, but would be fun to do.
Even though that seems like a lot, it's really cool if you think about it. Even if you have like, even if the grades with more than 20, a half a degree, you can take a roll of foil and fill it.
Yeah, so this was
So
kind of
that's the raise
fun.
at half a degree.
Yeah. All right, we'll finish the quantification sometime. So osmosis is just considered the flow of usually water, so the flow from a low concentration to a high concentration. And so there has to be some sort of semi-permeable membrane that would allow like water, for example, to flow through it. And so in this case, so we have our picture here. And there's our solute particles in here. So notice on the left side, there's something to be dissolved. And on the right, it's just pure water. And so initially, if you started in these conditions with a semi-permeable membrane, that would mean that the water would want to flow from this low concentration. So again, notice there's no ions here. So it wants to flow from this low concentration to a high to try to dilute all these particles and make these the same concentration. And so that water level would rise. And so you could, again, quantify this water level rising. So we mentioned somewhat pressure, and you remember the manometer, so we can do the same with water. And the pressure of this fluid then is related to the osmotic pressure of solution. And osmotic pressure would just be the amount of pressure that would be needed to keep that flow from taking place. So then we could pressurize this and prevent that flow. And so it is proportional to molarity. So this is a formula for osmotic pressure. So it's equal to molarity times R, which is the same gas unit, times T. So T is once again in Kelvin. So always in Kelvin. And really it needs a little I here too. So this is finding out the proper formula. And so you may also see it with a little I. And what the heck is this I? And all this means is how many particles it disassociates to. And, well, what do we mean by that? And so if we have a non-electrolyte, like sugar, well, we don't expect that to dissociate. So that just has an I, or Van Hoff factor of 1. But then if you take sodium chloride, right, sodium chloride, we know that splits into sodium plus our chloride ions. So for every, right, 1 mole, or every 1 molarity of solution, we really get 2 moles of ions, though. So that's this Van Hoff factor. So whatever your molarity is for like sodium chloride, you'd multiply that by 2. And all we care about is the expected. So notice this I measured would just be if you were like calculating this or measuring, quantifying this, you would find it's not perfect, but for our points, we're just going to do what we expect. So magnesium sulfate, again, we expect that to fully disassociate. So that makes 2 particles. So again, multiply times 2. Magnesium chloride, right, we get 1 magnesium, 2 chlorides. So that gives us 1, 2, 3 particles. And so I'll just write a 1 molar solution makes 3 molar of ions, is what all that is saying. So potassium sulfate, same thing, right? 1 molar solution makes 3 molar of ions. And then last example, right, iron chloride. Again, it disassociates into iron 3 plus 3 chlorides. So that's 1, 2, 3, 4 particles. So if we had a 1 molar solution, we have 4 molar of ions. And so last little bit is a bit of terminology. And so we have what, looking at different solution concentrations and like a cell. So for example, your normal red blood cell is going to be isotonic or isoosmotic. So these terms are used interchangeably. And that means it has the same osmotic pressure, aka the same concentration of ions. And so there is flow, right? But there's no net flow, so nothing's going to swell or nothing's going to shrink. So it's just going to stay that size. And if we have a hypertonic solution, or hyperosmotic, and so this means that the solution has a higher osmotic pressure, aka it's more concentrated. That means the poor cells are going to try to lose water to try to bring the outside concentration to the same, so try to make that isotonic, but in that process, right, your cells would get shriveled. So this would be the argument to not have too excessive of a salty diet, right? You don't want to shrivel up your cells. And then if you have a hypotonic solution or hypoosmotic, that means your pressure is lower than inside the cell, and so water is going to flow into the cell. And so this is the danger with doing like those gallon challenges, or like how people die on drinking large amounts of water. So it just so happens, you dilute your bloodstream too much and drinking all that water too fast, right? Your cells could potentially burst or anything like that. All right, I think that finishes the chapter. But then we could look at our homework. I just have to pull it up on here. Let's see. Let's just start with the first one. Well, one is pretty easy, but try like 2 then to start off with, and maybe 3. So it's just telling you, like, basically to calculate the weight per volume ratio of your naphthalene to your liquid here. And it may even seem like really simple, because it, like, you're not,
40 grams per volume.
yeah. Do we have number 2 yet? So I see one thumbs up. Do we get molarity, everybody else?
I don't know what the heck we're doing. Well, anyway.
What about number 2? So do you know what's going on?
No. I never got the one we did on the practice back here. How do we get the mold? Where's the mold?
So this is, right, where everything comes back. So we're given 10 grams though. So we don't need moles of chloroform. So that's fine if that's just in liters, right? 0.5 liters. So molarity is moles over liters. So we have 10 grams of naphthalene. They gave us a formula. So now we can calculate moles, right?
So the grams per mole is 608
You said molecular weight, right?
molecular weight of 1.2 grams per mole.
So does that help you? So, right, so we can't throw everything that we learned about calculating molecular weights and finding moles, right? We can't throw that out. That's going to be front and center still. So we could figure out how many moles first, right? So 10 grams divided by this.
About
0.0780, so that'd be moles.
Is that 128.2 or 7?
0.2. And you could have slightly different numbers with rounding, right? But it should be somewhere around 128.2. And then convert this to moles. Then you're ready to plug into this formula, which, again, you might want to write somewhere because this formula is going to be front and center as well. So now 0.078 moles over 0.5. So what do we get for molarity?
molarity equals 0.156.
Question?
128, was that the molecular, could you, I'm just confused by that.
So then you have to add all this up just like from the periodic table. So 10 times 12 plus whatever hydrogen is, so 1.008 or 1.01, however you want to round.
Okay, that would be your total grams per mole.
Yeah.
Oh, okay.
So then 3, don't let 3 confuse you, like all these weight volume things, so that just depends.
I guessed on that one. I just did grams per liters.
Yeah, exactly.
What does it say about weight?
You might want to do it in milliliters just to give you like nicer numbers, but your units would just be different and your number would be slightly different, I think.
Okay. Yeah, that makes sense.
Yeah, because if you did,
I ended up with 20 grams per liter.
Oh, yeah, 20 per liter, you're right. So either,
So for the future, if it does ask for something like that, try to switch it to like milliliters or something.
yeah, because what it's looking for is like some sort of percent, so it's looking for like smaller over larger.
Okay,
So that's why it likes the milliliter
okay.
units there, so then you can do it as a 2%, and they usually abbreviate weight per volume solution. And again, if you were to just divide, so 10 divided by 500 gives you that 2%. And again, it could be gram per gram, milliliter, liter. And so now figure this one out. So what volume of the solution contains 2.7 grams of naphthalene? You could do this a few different ways. Do we have an answer for 4? Maybe the easiest way to do it too.
I just was, I took the weight and tried to figure out the moles, so I had to substitute moles in, so we already had 128.2 grams per mole for the naphthalene, which I got 0.02 moles.
That's the hard way to do it.
Okay.
What-
Well, it is our way.
What'd you get for your answer though?
I got 0.135 liters.
0.135 liters. And let's set it up the easier way. So if you start with this, oh my gosh, sorry. You can just set up a proportion. Why is this being, okay, so 10 grams for every 500 milliliters. And so 2.7 grams is X milliliters. Of course, you could do it the moles way, but that was just a lot of work. Nothing wrong with it. That's so 2.7 times 500 divided by 10, and so that gives you the same answer of 135 milliliters. And you could do the same thing with 5, so just a proportion there. Or do a molarity moles calculation. So you have molarity, and you could figure out moles from there, but that's probably more tedious. All right, we should probably stop since we have our quiz. So any last minute questions before our quiz? So like I said, I'll hand back lots of papers, so double check your grades as well. And make sure I entered everything correct and papers aren't lost somewhere. And, yeah, we'll take our 10-minute break though and then come back for a quiz.